Hi, everybody. So, this lecture, relays and controls. Basically, we're going to be talking about relays and in what ways they control stuff. And so, naturally, let's start off by talking about electromagnets. Now, we're going to get more into the principles of how magnetism and electrical magnets, or electromagnets, pardon me, how they work in the magnetism module. But when we put current on a wire, a little magnetic field develops around that wire. So this is a coil of just some bare copper wire. And when this is actually the a chime unit with the cover taken off, I should specify. And so when we put current on this wire, it makes a little electromagnet right here. And this metal plunger will move based on just the opposites attract or same poles repel of a magnet. So by using magnetism, we're going to send this plunger up. And this diagram is actually a little bit misleading. We've been talking about drawing things in their de-energized state. But looking at where this plunger is, it's actually doing its bing. It's hitting this metal plate, so it's making a noise. And then the spring is going to, because the spring is stretched out, when the magnet stops doing its magnet thing, this plunger is actually going to go down and hit here. You can probably almost see a dot right here where it's hit. This is hitting a little stopper here. So we talked about, at the end of switching circuits, we talked about a chime unit or a doorbell setup where one plunger goes bing bong and the other one goes bong. And that's exactly what's happening here. There's a little stopper here stopping this guy from hitting this top bing unit. So he'll only hit the bottom. And the spring will send it down. Now here's sort of a cross-sectional diagram of what's going on there. So this coil of wire is basically, if you want to think of it, it's coming, in the real world, it would be coming out of the page and going back into here. Coming out of the page, going back. So it's wrapping around this plunger many times. And this travel stop, once again, is the thing that stops this plunger from flying out this way. And then there's a metal frame to kind of keep it all together. So let's start looking at some relays and start talking about figuring out why I've been talking about electromagnets. Now, we have three types of relays here, and a relay kind of works in a switching manner. Now, up here I've drawn what's called a form A contact. A form C contact would look more like this. So perhaps I should actually, apologies, this should actually be just a line here. This would be a form B. And then a form C contact has a bit of both. So those are just examples for what's going on. Now, this relay is a pretty simple one, and the diagram or the picture on the side here explains it really well. This is our coil, and this is our two open contacts. Now, basically, if this was the coil, we would bring our control wires, or the wires we're using to control the relay, here, and then we would bring a common wire, or we would feed one side of these normally open contacts, and we would go out from the other side to the load. This relay actually has 4 commons and 4 outputs, if you want to think of it that way, because it has a normally open, a normally open, a normally closed, and a normally open. Now the A1, A2 are for the coil, and you can look at this diagram more closely in your module, but basically right here is the coil. So A1 would be here and A2 would be here. The common, or 44, would be this down here, and then the normally open, numbered 43, would be up here. Of course, the only different one being 22 and 21, which is here and here, and I'm not sure if you can see it in the camera, but this is normally closed up here. Now, these are the relays we're dealing with in the lab. They have a coil rating, and then they have a power rating. It just says the rating. Basically, relays are sometimes confusing to read when you pick them off the shelf. This one here is straightforward. It says coil is 120 volt AC, 50-60 hertz, and then it has these other ratings for the contacts. So these relays, usually the power contacts, which would be here, which would be our Form C contacts, are labeled on the face. And sometimes the coil is, sometimes like the ones we have in the lab, you have to actually look inside of this clear plastic to see what the coil's rated as. But if we look closely, this bar coming down here would be our common, and we can see it touching the normally closed, and then we can see it not touching the normally open. So pretty swell little demonstration to learn how to use relays, these guys. These are normally called ice cube relays in the field, just because they're kind of transparent and in a square type shape. But relays are, when we draw them in our schematics, relays are loads, or we draw them as loads for the most part. And it might make more sense as we start looking at some schematics. And so here is a breakdown of the parts of the relay. So this is the connection for our coil. Excuse me. And then this would be our Form C contact. So normally closed, this coil is not energized. And so this is normally closed, and this is our normally open. Now, what happens and how this works when we send the appropriate rated voltage to our coil is it's going to send current, and there's going to be current flowing on these wires. And these are wrapped around this core. So as current flows through these wires, once again, it makes that little magnetic field, just like our doorbell chime unit, just like the solenoids on that doorbell chime. And that turns this core, that magnetic field, it turns this core into a magnet, which attracts this armature. Which closes the normally open contacts and opens the normally closed. So, once again, we energize the coil, we send current to it, we create a potential difference on either of these terminals. That potential difference allows current to flow, which turns this relay coil and this core into an electric magnet, or an electromagnet, which then pulls this armature to here, changing the state of both of these contacts. And then when we stop sending current through here, and this stops being an electromagnet, the spring pulls it back the other way. So our load is going to be taking current through this armature and going out through the normally open contacts or to the normally closed contacts, depending on if the initiating device is doing anything to this coil. Now, because we need an initiating device to make this relay work, because if we hooked up a relay to constant power, it would work once, and then we'd have to de-energize the circuit just to make the relay work. So this is why I was saying a relay is a load, but it also has a switching function over here. So they're kind of unique in that aspect of our schematic diagrams. And so this is a simple and practical use for a relay. Now I'll tell you ahead of time, this is a great explanation for a relay working. You would probably never see this actual circuit installed somewhere. It's a little bit impractical, but we'll figure out what I mean by that near the end of the lecture, or hopefully we all figure it out by the end of the lecture. But the reason I say that is just real quick. Let's go through what's going to happen here and what's going on with this wiring diagram. So we got 120 volts coming in over here. It's transformed to 24 volts. That's well. I know that this is AC because you do not transform DC. DC cannot be transformed. Okay, and we'll learn more about diodes and stuff that sort of simulates DC when we get into extra low voltage switching. But we only transform alternating current, not direct current. So that's just a little extra explanation. So we have X1, we have current coming down here, and it'll stop here. The push button is not doing anything, so nothing happens. Everything's in its de-energized state. The lamp is not on because it's not getting current through. It's open. These normally open contacts are open. So this circuit's not complete. This circuit's not complete. So I walk up. I want to turn the light on. I push this button. So push this button, sends current through, energizes the coil, turns this whole thing into a magnet, which pulls the armature. The normally open contacts become closed, allowing current through L1, through the armature, down the common, up to the lamp. Bing, lamp turns on. It's putting out all that awesome light and heat if it's incandescent. And then the current has a way back to the identified. Now, there are two problems with this diagram. The second one, kind of a minor one, is they labeled this L2 when actually it should be the identified. The bigger problem, and I have actually written the ILM board, but that probably doesn't interest you very much. The bigger problem here is what we actually do in the field. And what you do in the field is you take this L1 and you don't go to the normally open. That is not how it is done. You take this L1 and you actually go down to the common terminal. Now the reason we do that is not only is it best practice, because if you ever wanted to use this normally closed, for example, you walk up, you push this button, the lamp turns on, you let the button go, you see the lamp turn off, you go, oh, okay, so power's going through here to the lamp. But if you hook up something to this normally closed, it's never going to get that power if it was hooked up to the normally open as they show it in the module. So when we're bringing our power circuit to our Form C contact or any contacts of a relay, the power circuit goes to the common first, and then from either the normally open or the normally closed out to our load. So hopefully that makes sense. Hopefully I didn't cause any extra confusion with my disagreement with the module. Now, how they have it drawn in the module is still going to function electrically speaking. It'll still, this will close, current will still flow through and out to the lamp and back on the identified, right? That'll still function properly. But I wanted to point this out because in the field, how they have it drawn in your module is not how it should be in the field, and it's not what you should do when you're wiring relays in the field. Now, one final note on this wiring diagram. Notice the 120 volts for the lamp, which is pretty common. That shouldn't be anything new to us. But the 24 is for the coil. Now, if you've ever heard a relay chattering, what's happening is either usually too much voltage or there's some problem in the relay. But that chattering is this armature just going back and forth. So if this coil is meant to take 24 volts and you put 120 volts on it, it's going to pull that armature, it's going to push it, it's just going to start spazzing out basically because it's not what it wants. It wants 24 volts. So don't mix up your power circuit and your control circuit, even if they're the same voltage, but especially if they're different voltages. Do not mix up these two circuits. So here are some symbols, some correct schematic pictures. Now, a couple new ones here, or somewhat new to us. The transformer, that one's particularly new because usually we're using 24 volts on our control circuit of the relay. The bell and buzzer, sort of straightforward. The bell rings, the buzzer, buzzes. They both make noise. They're audio devices or audible devices. The light, hopefully by this point in the course you know what the light is. Then we have our normally closed contact and our normally open contact. Those are new for the relays. We have our symbol for a control relay. So it's just got the CR in a circle. Hopefully we remember what the single pole, single throw switch is, and these are our 3 different push buttons. So here's our wiring diagram of our relay controlled by a push button. Now, the reason this is a wiring diagram is because it actually shows where the wires are terminated. It also shows, in general, the physical location of things. So we have a source up here, we have our lamp, we have a wire coming to the lamp, we have a wire coming back from the lamp. This isn't exactly where everything would be in the field, but it does show relative physical location. Now, I'm going to label the terminals of this relay, and this will make more sense as we go through the lab. But our coil is usually 2 and 7. It could also be A1 and A2. Just sort of depends on the relay base, because we plug a relay into the relay base, and the base functions as a holder for the relay, obviously, and also it functions as a place to terminate all your wires. Now, some relays are all in one, some have a base that you plug in different relays to. And then we could also label our common is 1, or, as you'll see in the lab, it could be 1 or 8. And the normally open is probably 3, and our normally closed is going to be 4. Or, if we're using the 8 terminal as the common, the normally open would be 6, and our normally closed would be 5. Now, if I were to put the power wire, and once again, this is drawn incorrectly, but if I were to put a power wire to common terminal 1, and then try to switch my load coming from normally open terminal 6, it wouldn't work, because the relays in our lab have 2 Form C contacts. And as we draw our schematics, it's important to label those different contacts so we know what's what. Can't just assume that, well, I know how I wired it, so it makes sense. Relays, as we start to draw them and work with them, our labeling is going to start to become very important. So if I wanted to label this correctly, I'll take out these numbering Form C contacts. And so now my wiring diagram, I could just take it to the field. I could take my wire. Oh, hey, I have my push button. Okay, I just need a wire to 2. And then 7 goes back to my 24-volt transformer. And then I look and say, oh, this diagram is backwards. I should actually take 120 volt to the common, and then from the common being number 1, and then from number 3 go down to my lamp, and then from the lamp back to the identified. So that's a wiring diagram. That's kind of our first real taste of wiring diagrams. Now this is neither a wiring diagram nor a schematic diagram. It looks like a schematic diagram, but it's using the wrong symbols. So it's not quite right, but it does. This one helps us conceptualize that wiring diagram into a schematic diagram. It's also a good way to look at relays as a load device, even though up here they're drawn to the left of the lamp. So this normally open contact is sort of functioning as a switch, but the coil is going to function as a load. The coil gets controlled by the push button, and then the contacts of the relay control the lamp or allow current through to the lamp. Now, the correct schematic diagram would look like, let's get my papers organized, would look like this. And so now this is maybe a bit more familiar to us. We've done quite a few schematic diagrams, especially with the switching circuits lab. So now we can see I push this button down, it sends current to this relay. The wiring diagram we looked at kind of shows us the inner working parts. And so when this relay is energized, because right now how it's drawn, it's de-energized. So if I were to push this button down, making this contact, sending current to this relay, it would then close this contact, the normally open, and send power through to the light. And as long as I keep pushing this button down, this relay has power, its coil is energized, it keeps the normally open closed, and this lamp stays energized. Sweet. So all I have to do is just stand here until I don't want the light on, pushing this button, and the light will stay on. Obviously, I don't want to do that. I mean, maybe it's because I'm lazy, maybe it's because I have better things to do. Who cares? For whatever reason, I'm going to say, you know what? I don't want to stand here holding this button. I'm going to see if this relay will actually do some work for me. We'll cover my shift of button holding. So, what kind of witchcraft is this? What's going on here? Now, if I were to label these, and this might help us understand, because these are both 24 volts, both of these branches, I could actually just use one contact, but I'm going to label this how we normally do, because normally this light would be 120 volts. So I'm actually just going to dissect it like that. I'm just going to say from here to here is 120. So now I'm going to be using 8 and 6, and this is how you label your schematic diagrams. And up here I'll use 1 and 3. And so 1 is a common and 8 is a common. But I do not want to mix up. I don't want to send 120 volts to this relay. I mean, it would work briefly. It would chatter and this light would flicker and then the relay would smoke and everything would stop working. And then 2 and 7 would be the coil terminals on my relay. So I have everything labeled. And how this is going to work, and the reason that the relay is now going to cover my shift of button holding. When I push this button down, this relay will get energized. And what will happen is it will actually close this contact and it will close this contact, right? These are both normally open contacts. Now, the light turns on. Perfect. That's what I wanted to do. But the relay also stays energized. When I take my finger off this button and the normally open button returns to its normal state, this relay will stay energized because current can continue to flow through here. If I were to push this normally closed button, it would break the contact between these two terminals. The relay would become de-energized, and both of these contacts would open back up. So this guy right here is called a holding contact. It basically holds the relay in its state. It holds it in its energized state. And so now I don't have to stand there all day holding this button to keep the light energized. Now I just press it once, relay energizes, closes here, turns the light on, keeps itself on, and the relay says, I got you. Take the day off. You don't have to hold that button all day. Come back at the end of the day, hit this button, I'll turn off. That's it. That's your whole shift. So that is what we use holding contacts for. Now, normally we would call this a start button and this a stop button, but that does not always have to be the case. And I've also been talking about putting control devices in series with the load, but you'll see that this contact is in parallel with this push button, which makes sense. If it was in series, it wouldn't actually work, because once I take my finger off this button, the relay would be de-energized. Now, if I wanted to add another button, maybe I want to turn the lights on from somewhere else, I would put the normally open button up here. And there we go. I can press this button or I can press this button. Either way, current has a path, or once I push either button, current will have a path through to the relay, energize the relay, close this normally open contact, close this normally open contact, turn the light on. I take my finger off this button now. This contact is still closed, and the light stays on. Now, if I wanted to add another normally closed button, I would put it in series. If I put another normally closed button in parallel, and this light was on, and I wanted to use this button to turn off the relay, when I push this button, the current still has a path through. So our stop button, which are almost always normally closed, so let's just say this is our stop button, these are our start buttons. Our stop buttons are in series with each other, but our start buttons will be in parallel with each other. However, all of our control devices as a group are in series with our load devices. That's still true. Now, we're going to start to look at supervised and unsupervised circuits. And basically we use relays to create those two types of circuits. Now, if you think about a supervised exam, when you write a supervised exam, you're basically being watched the whole time, or there's someone present or something present. Now, if you're writing your exams online, there's a webcam watching you the whole time. So you're being supervised. If when you go to write the TQ, there's a bunch of people in that room supervising you. You're being watched all the time. And so this supervised circuit is, we're going to start to look at this circuit. And what I want us to start to or what I want you guys to start to do, is analyzing your circuit. You're given a circuit, look at it, recognize what's in this circuit, what's the voltage, recognize everything that's going on, and start to analyze what's going to happen in this circuit. So, when I energize this circuit, I go over to the breaker, turn the breaker on. Buzz, this is going to start to buzz. This is our buzzer. It's going to start to make noise as soon as I energize this circuit, because there's a path for current to go through this normally closed contact. So when I just turn on the circuit, current goes through this contact to the buzzer, and it starts a buzzing. Now, I'm irritated by the buzzing. I walk over to this switch. I close this switch, energizing this relay, opening the normally closed contact. So once again, turn the circuit on. Current goes through the normally closed contacts to the buzzer, making that awful buzzing sound. I close this switch, energizes the relay, opens the contacts, and now the buzzer stops. Now, the reason it's called a supervised circuit, and the reason I said it's always being watched, if anything happens in here, if someone just walks by and goes, you know what, I hate electricians, I'm going to cut their wires, and they cut this wire, the relay gets de-energized, which closes this contact, and this starts a buzzing. So this is always supervised. Now, if you were to cut a wire up here, obviously the buzzer would not work. So if this was a life safety thing, like a fire alarm, and you had a battery backup inside of here that said, hey, if I lose 120, switch over to the battery power and start a buzzing. Because if this is life safety, that means it's life and death. I have to have this device working. But in this situation, it's just a supervised circuit. If someone came in and said, I'm going to replace this relay, it's going to start buzzing as soon as you pull that out. It's a supervised circuit. It's always watching. So now I have an unsupervised circuit. This is my beautiful drawing. I drew out both of these circuits. You'll notice 2, 7, 8, 6. The last one was 8 and 5. So let's start to analyze this circuit. Now I'm going to walk up. I look at this circuit. Okay, I got some normally open contacts. I got a buzzer. I got a switch. I got a relay. Now these contacts are labeled CR, so I know they're for the control relay. If I had multiple relays, I would need to start to number the relays and number the contacts, so I know which is which. I see that these are normally open. So now I know when I turn the circuit on, no buzz. This buzzer does not get energized just by turning the circuit on. But if, for example, I wanted this buzzer to go, if this switch was labeled, hey, hit me if, switch me if something bad happens and everyone needs to be notified by a buzzing. Now I walk up, hit this switch, energize the relay, close these normally open contacts, which then allows current to go through to the buzzer, and it starts a buzzing. Now, the reason this is unsupervised is not only because this is a normally open contact versus a supervised that had normally closed. If I lifted this switch, if I turned off this switch, the buzzing would stop. If I closed this switch, turned the buzzer on, and cut a wire, the buzzing would stop. It's not supervised down here. We don't know if this part of the circuit is even still functioning. So that is the unsupervised circuit. Basically, someone can come down here, mess with stuff, and we don't know that this part of the circuit is being messed with. So that is the unsupervised circuit. Supervised and unsupervised circuits are a great way to start to analyze circuits, which is an important skill for any electrician in basically any specialty of the trade. And once again, send me your questions if you have them.